Cool. So good to see you, everyone. Today, we're going to talk about private payments. Personally, I didn't really know private payments, even though I've been working in ZK for a while. That's not the big thing I'm in, I guess. So preparing for this talk was actually interesting because I saw that there's many different papers, many different approaches. So I have a list here. But I think what would be fun would be to create a list together to begin with and try to make it interactive and see if you guys know something that I don't first, like maybe a cryptocurrency or something like that. And then we can try to talk about them. So I'll start because that's the first one that I learned was Zcash. And I guess I could go further, but maybe just you guys throw like names at me and I'll start writing them. Monero. So I guess that's the one I wanted to write as well. Yeah, when I started, these two guys were, I guess, up there, and I thought they were like the first scheme to come out, but then I realized.
I think Aztec too, you can do shielded stuff.
Yeah, Aztec. So, and then we can try and categorize them. Maybe I'll put it there. So Aztec network, very similar to Zcash, so we can say that. Yeah. Anything else? Mimblewimble.
MobileCoin extension /
Mimblewimble. What was the second one? Oh, did you say something or?
Oh, nothing.
Oh.
Railgun, I guess.
Railgun. I don't remember how this one works. I think it's like Monero.
Oh, it's like Aztec or Zcash.
Oh, it's a shielded pool?
Yeah.
All right. All right, I've heard about all of these ones. Maybe someone can come up with something I haven't heard before. Tornado Cash, so same as Zcash. Tornado Cash. We don't have to do that for too long, but just to get some stuff started.
So I don't know if Maiden does similar things, but they have similar.
I think Maiden is a shielded pool, so I would put it here. I'm pretty sure that's what they do, but yeah.
I think Maiden may actually be kind of like Mina, where it doesn't really like enforce a specific state, but like the contracts can do their own.
Well, I know they were like dealing with nullifiers, so I figured, or maybe it's one of the app on Maiden. Actually, that would make more sense. All right, maybe one last one.
Prevedium, it's guessing.
Prevedium?
Yeah.
How do you spell it? Like this?
Yeah.
All right. So is that like Zcash on ZK Sync or something like that, or?
No, it's just ZK Sync, layer 2 private, layer 2 stack.
Okay. I guess this one I don't know. Cool. So we're not gonna talk about any of the. We'll talk about some of these later, but I'm gonna start with the very first one. When I started looking into that, I realized that I think in 1982 or 1986 or something like that. I don't want to be wrong, but if someone wants to correct me, they can. David Shom was, I believe, the first one to introduce something he called E-Cash.
I think that was 1986.
86? So I'll put a 6 here. And if someone wants to correct me again, then. And I think that was the first proposal. So it sounds like maybe you would know. And interestingly enough, there was no ZK in there. So it was purely blind signatures. And he introduced blind signatures as part of this thing. So maybe I'll use a different color. And maybe there's two other things that are interesting is that at that time, they didn't really think about cryptocurrencies and decentralized systems and these kind of things. So they were in mind, they had this idea of like working with banks. So it was relying on bank, like a centralized bank, like a central bank. And they also had David Shom, I guess, was like, I don't even know if that's how you say his name, but always had this idea in mind that you had to like do something that was regulation friendly and compliant with whatever were the rules. And that's something that kind of disappeared after, like when all these cryptocurrencies started introducing new private payment system, they sort of forgot about all the auditability and regulation friendly and all these kind of things. And now it's making a comeback. So we're seeing more and more like private stable coins that are regulation friendly and trying to play with that. I guess I can briefly explain how that works. But the way it works is that, oh, and if you don't know blind signature, well, I'll explain that as I go through that. So the way it works is that imagine that Alice wants to get in this world of private payments. Alice goes to the bank, she creates a random string, and she asks the bank to sign it. So I don't know. Let's call it coin 1, but imagine that this is a random string. And then we have, let's say the bank is here. So she sends that to the bank responds with a signature over C1. So it signs the coin saying, yeah, okay, you gave me some real fiat money. I'm going to give you a signature of this coin. And now you can use it in our world. And now if Alice wants to spend the coin, she can give that thing to Bob. So she gives the sign UUID or like random string to Bob, and then Bob can go to the bank and like exchange it against money. Now this wouldn't be very secure because like you can everything's in the clear. You can see who Alice is. When she gives it to Bob, then the bank can see that it's the same coin that they initially gave to Alice, so they know exactly who she gave the money to. So by itself, it's not great. So what we're gonna do is that Alice is gonna basically blind the coin when she creates the coin. The bank knows that she gave some fiat money to the bank, so they're like, sure, we'll sign whatever it is, but we don't know what it is, it's blinded. And now Alice can basically, then Alice can unblind the thing, and she's left with a signature of the coin. And that she can give to Bob. The bank doesn't know what they already signed, so they're not gonna recognize that this was the coin for Alice, and Bob can use it. Does that make sense? So this is what blind signatures are. Basically, you're getting someone to sign something, but they don't know what they're signing. Well, so any question on that? And also, can someone tell me what is wrong with that scheme, or like what is there a vulnerability, like an attack in that scheme?
You have to trust the amount, right?
So in this system, every coin is the same amount.
Oh. Okay.
So that's a very trivial system. Every coin is the same amount, and the amounts are not encrypted.
Is it actually atomic though, like the swap? No.
It's, I guess in what sense?
You can double spend here.
Yeah, that's what I.
They have to sign the same.
You can double spend it?
I mean, if the bank doesn't know what they are signing, you can take them to sign the same.
So, oh yeah. Okay, so the bank,
It's some sort of attack.
So here the bank knows that it signed something, a coin, right? It hasn't been spent yet. If Alice gives that to Bob and Bob presents that to the bank, then they allow Bob to spend it, to convert it back to fiat. But the bank will have to record this thing. So the bank there's this notion of like, I guess, same as nullifiers that we'll see in the future. But there's this notion of like the serial number or the signatures that the bank has to like keep track of to make sure that there's no double spending. All right? So, oh no, I can write that. But yeah, Bob will come here, present that to the bank, the signature of C1, and the bank will give actual dollars, But the bank has to remember, whenever you see C1, it's already been spent. Does that make more sense? So there's no double spending issue, there's another issue though.
They can link it back to Alice?
They cannot, because they didn't see the actual value of C1 here.
The issue though is you have to trust the bank. That's the issue.
You have to trust the bank. So that's the centralized system.
Yeah,
That's an issue. There's another issue. There's many issues.
Scanning all those tags.
Scanning all the what?
The serial numbers.
You're just collecting these, I guess, serial numbers or like whatever you want to call it. You're just collecting these signatures, so you're seeing what is being spent, but you don't know where it came from. What we're really masking here is not who received the money, because Bob will have to like show the thing at some point to get the money back. What we're hiding is the linkability between the creation of the coin here between Alice and sending that to Bob. So I guess the term is linkability. Maybe I'll write it down. or up here.
Oh, you can't have multiple. You can't really handle like. You can't verify like too many.
No, let's imagine that you can, like, you're not limited in term. So okay, I'll give you the answer. The answer is that when Alice created the coin C1 and she gave it to Bob, she can still spend it because she knows the signature of the coin. So if Bob doesn't spend it, she can spend it before Bob and basically double spend it, right? She gave it to Bob. So the way these schemes work is that when Bob receives this thing from Alice, he has to spend it right away to create another coin right away so that Alice cannot spend it. So that was one of the limitations of that scheme. The other thing, I guess, that I mentioned also is that we're not masking the amounts. So the amounts are in the clear, and we're not really masking who is the sender. And you'll see that basically, I guess there's different way to look at these things, but you'll see that sometimes we're masking the link in a transfer, like we're trying to break apart who receives, who sends and who receives, like in a group of transaction. Well, maybe I'll talk more about that later. Sometimes we're trying to mask the amounts. Sometimes we're trying to mask who's sending. Sometimes we're trying to mask who's receiving. And you'll see different systems that do some of these or all of these. Okay, so, maybe briefly I can explain how blind signatures work. If you think of a RSA signature, like you have a message, and to RSA sign it, you raise it to some exponent, mod n, I guess. The way you would blind this RSA signature is that before it gets signed here, you would first raise it to some blinding factor B. Someone signs it, so you get B times S in the exponent, and then you raise that signature that you just got with the inverse of B, 1 over B. The very quick explanation of how blind signatures work.
And what is the result of that? Is that cipher type?
The result of that is basically these cancel and you just get the signature of M.
Oh.
But since you blinded it, the signer would only see M of B. A pretty simple concept. All right, let's move on because I don't want to talk too much about this one. So this concept of blind signature is interesting. There's a few other developments that I've seen. There's UTT that basically decentralized the bank. And so they can't use blind signatures for that. So they use something called randomizable SIGs. But it's somewhat similar. They know exactly what they're signing here, but then you can randomize the signature so that when you spend it, it looks like a different signature. So they cannot recognize this thing. That's all I say about that. And the other one that I found interesting is Zether. And basically, they sort of go one step further. They're like, okay, we can decentralize it, but we don't even need a consensus. We can use this thing like that's weaker than a consensus reliable broadcast. And so they sort of shard the states and they make it very efficient. And yeah, basically. But there's many systems that use blind signatures, and there's many systems that use these Chaumian coins, as we call them. The other thing maybe I should mention, I can mention it at any point in time, or maybe I'll mention it after because here we haven't really masked the amounts. All right. So maybe now let's talk about Bitcoin. Bitcoin came and they talked about this notion of pseudo-anonymity, where sure you have accounts and addresses, we don't know who they are, but really we can see graphs of transactions. Like we're not masking the graph. And so maybe at some point we can guess like who is who on this graph, and then you're de-anonymizing people. I think there are like a few rules that you can use, but generally, like when you do a transaction in Bitcoin, in this UTXO world, you always you have these notions of public keys. And so if you're reusing a public key, you know that it's the same person, most likely. And the other thing you can do, for example, is that when you see a transaction, usually people send an output that's going to be the change. And so if that change is reused after, you can pretty much track the transactions of the same person across the graph because they keep reusing that change. But yeah, there's many ways to like de-anonymize things on Bitcoin. This is on-chain. And maybe I can also mention this thing also, but remaining private is not just an on-chain protocol thing. Like you have to, like when you interact with nodes and all this machinery, you need to mask your IP. Depending on the size of your transactions, people can sort of de-anonymize you. There's many de-anonymization techniques. And it's actually kind of a nightmare. I mean, this is why Tor was invented. We had like, there's a whole literature on the subject about mixed networks and these kind of things. If you really want to be private, using a privacy coin is not enough. You should really have some OPSEC and make sure you're not leaking your IP address and these kind of things. All right, I mentioned that. I can cross that. I didn't want to mention it, but I mentioned it also. Like, there's also the idea of like if you're a wallet, you're a light client, and you don't really want to like run a node by yourself, and that's going to become an issue. Also, we're going to see in Monero. But even in Bitcoin, like you don't really want to like scan the blockchain and run a full node, so you'll query other nodes. And they had this system where to prevent other nodes to learn about what your address is on chain, they would give you a Bloom filter, and this would allow you as a node to like think that a bunch of transactions are probably relevant to you and give you all of these transactions. And so you sort of get some anonymity because the transactions that are relevant to you are part of other transactions that are not relevant to you. So Bloom filter is like a hash function that tells you hash something and it tells you relevant, not relevant, but it's kind of fuzzy. I can write it down. It's not very relevant to today's talk, but I guess this is interesting. The thing I think that's more interesting is CoinJoin. And I'm surprised nobody mentioned it. But I guess this, like if you're in the Bitcoin space, it's the more famous way of doing privacy. And CoinJoin is like, it works on top of Bitcoin. You can do it, like there's no fork needed. And it's a very naive idea of like, a transaction has like some inputs and some outputs. And it's leaking all of that. But instead of doing that, we're gonna get in a room all together and we're gonna create a transaction together where we're gonna mix, this is my input, my outputs, but we're all gonna mix like other people's input and output, and we're gonna create a transaction all together. And when we send that on chain, then it's not clear for people exactly whose inputs link to what outputs. So a CoinJoin is just about linkability. You're not masking the amounts. You're not masking who the sender and the recipients are. You're just like fuzzing this linkability. It's really hard to understand what output came from what input. Does that make sense? So that's kind of annoying because we all have to get in the same room. There's interaction. I learn what your inputs and outputs are. So there's like other ways to do it. There's like centralized protocols where you only have a trusted party. Then you can decentralize that guy. And there's many, many schemes. I don't really understand all the subtleties of all the different schemes, but people have come up with like ways to use blind signatures and shuffles and all sorts of algorithms to make sure that you can do that in a non-interactive way and nobody learns anything. But at the end of the day, it's really the size of your transaction kind of tells you like how are you like mixing yourself in this point in time transaction. And a CoinJoin is basically, I think you can generalize it as a mixer. And a mixer is basically, it's a very weak ID in a way because it's a point in time ID where you're gonna enter a mixer with your money, like everybody can see your money, your tokens. You're gonna enter the mixer and your tokens are gonna be like centralized in some place with everybody else's tokens. And when you're gonna get out of the mixer, it's not gonna be clear who's going out of the mixer. And same here, you have de-anonymization techniques. Like if you enter with the same amount that you exit with, then it's you. But this idea of mixer, you end up having them all over the place. We mentioned Tornado Cash earlier. So it's a mixer in Ethereum.
There are other like Bitcoin wallets that have
Right.
transactions.
Yeah, I've heard of like this kind of CoinJoin being implemented like as part of the wallets. There were so many projects I didn't even want to dig too deep into that. But all of these have to work with the limitations also of the cryptocurrencies they're starting with. I think you can think of like central exchange as mixers. So when you enter Coinbase, nobody can see what you're doing in Coinbase. You're like mixed with everybody else's wallets. Of course, you're trusting Coinbase, but it's sort of mixing you from the point of view of other parties. You can think of L2s as mixers, like if the L2s just do state transitions without really revealing what they compressed inside these state transitions, then you can think of them as mixers as well. The dumbest idea, the most naive idea you can think about is an L2 that just says, trust me, bro, like very centralized L2, and then nobody would really see outside of that L2 what's happening. Yeah, does that make sense? Yeah, I'm going kind of fast, but these are not the most interesting ideas. I mean, these are interesting ideas, but there's like a lot of interesting stuff. So again, we're not encrypting anything, right? Like amounts are in the clear, that's okay. There's a paper that comes up at some point, I think CT, so CT is CTCA, Confidential Transfer, Confidential Assets, came out in 2013, I think. I'm not gonna say any name every time because I never remember the names. I think it's Gregory Maxwell, but I'm not even sure of that. And these guys like, okay, coin join are interesting, whatever, but this unlinkability, like sure, you can do that, but what I'm really interested in is encrypting the amounts, like masking the amounts. And obviously you cannot do that on Bitcoin because everything's in the clear. But so they imagine what could Bitcoin look like if you were masking the amounts. And okay, question for you guys, like, can you imagine what primitive they use in cryptography to mask these amounts? There's one primitive that basically everybody uses to mask amounts. Commitments? What kind of commitments? Which one?
What do you mean by what?
Well, there's many commitment schemes. Pederson commitment, yeah. It's just a funny question because in theory you could use a lot of different commitment, but these one keep coming back for some reason.
Oh, I've never even heard of that kind of commitment.
So that's basically, yeah, you can think of every scheme using these, and it's very easy. You just use, imagine you have a balance, V, and you want to encrypt it. So the additive way of writing that would be that you raise, you scale multiply like a elliptic curve point, I guess, with that. And then this is not hiding, so you take your, this is R, by the way. I know it looks like my V. You take a blinding factor and you raise it to another. Actually, I'm going to use H because a lot of papers do that. And here you're going to use a different base. You can also rewrite that as a, some people would write that in multiplicative notation. Just if people are used to that, like you can see them as the same thing. So, and the only thing you need is you need groups that are big enough, and you need them to be, you need to not know the discrete logs of these two guys, and they have to be different. But it doesn't matter too much. This is what a Pederson commitment is. And this part is always annoying, but it's the blinding part of it. So if you want to open this thing, you need to reveal the value and the blinding factor. And so what CT, confidential transfer or confidential asset does is that they say every transfer is gonna, or every amount in like these UTXOs and inputs and outputs, whatever, is gonna be a Pederson commitment. We're gonna know who's sending the tokens, the Bitcoins, we're gonna know who's receiving Bitcoin, but we're gonna mask the amounts. So really seeing different combos here, right? And so the only thing you need to prove, or there's two things you need to prove, is that the sum of the inputs is equal to the sum of the outputs. It's a bit different than that because you need to introduce fees. And so if you want to write that as commitments, that makes sense, right? The sum of the input needs to be equal to the sum of the output. You're not creating money. Unless there is a reward, unless, if there's some fees or reward, block reward, whatever. But with commitments, this equation becomes something like that. Be like this, maybe. Oh. I don't know if that makes sense. But you're basically getting a bunch of commitments on the left and a bunch of commitments on the right. And if you're not creating any money, then you know the V's are going to cancel. And if you're reusing blinding factors in a good way, then these guys are going to cancel as well. Does that make sense? You don't necessarily need to reuse commitments in a way that these cancel the blinding factors. What we're going to see is that what a lot of people do is that this gives you like you get some result at the end, that's the commitment to 0. So you get a blinding factor. That's the accumulation to all the blinding factors. And then you can use that as a private key. Maybe I'm not going to explain that now, because I don't think that's what they did in the paper, but I'll explain it later. I'll come back to that. So for now, I'm just telling you people are using commitments instead of values, and you can check without opening these commitments that the sum of the inputs is equal to the sum of the outputs, thanks to the homomorphic property of these commitments. So we can add them, and it preserves what's inside. The other thing that they had to do was to introduce range proofs. You don't want things to wrap around. So you need to prove that the values you're creating here in the outputs are in a specific range. So usually you accompany that with some zero-knowledge proofs that these things are in a range from 0 to 2 to the 64. So they're 64 bits values, because we're in this field and things wrap around. I don't remember what range proofs they started using, but you'll see that a lot of these schemes end up using bullet proofs, for example, and these kind of range proofs to prove that something, commitments is inside some range. There was another thing that was interesting. Oh, actually, any question on that before I say the other thing? Yeah, I mean, I guess if you haven't seen these Pederson commitments before, it's a bit confusing to think about them, but just the arithmetic really plays well every time you use it. The thing that they introduced was also the CA part, confidential assets. And I've seen that in Penumbra. I'm guessing Zcash must be doing something like that, but I don't know. And basically this H here, this generator, is a hash of like your token ID, I guess. By the way, am I in front of the... So you basically produce the generators to mask the values as a hash. So it's a hash to curve, because remember we don't want to know the discrete log here of some token ID. So it could be like the name of your token or whatever. And by doing that, it means you use a different generator for different tokens. And so these guys, where are they? I'm missing an H here, right? These guys will only cancel these guys if they use the same generator. So you have an equation that's canceling everything per token as well. All right, that's confidential transfer, confidential assets, and I just wanted to use that as an example to introduce Pederson commitments that are going to be used everywhere else. Every time I'm trying to remember of like a scheme that doesn't use that. Most of the schemes that we're going to look at use Pederson commitments to mask things. Maybe not the FHE stuff if I have time to reach that, but...
I mean, I guess the original Zcash.
I guess they don't say what commitments they use, maybe? I don't remember.
Sprout does something.
Oh, right, they came up, I remember Dara actually was like, oh, we can use Pederson. Oh, no,
Yeah,
she was like, we can use Pederson hashing, actually. Anyway, maybe at some point they were not cool. So I can talk about Mimblewimble a bit. I don't want to get too much into it, but I thought that was really interesting. I don't remember when that paper came out, but I remember that it came out on some RSC channel. There's this guy that came out, and it was called, it was the French name for Voldemort. Yeah. So Jedusor is the way you say it. Tom Jedusor? Are you French?
No.
Oh. Oh, nice. And so yeah, so it must have been a French guy or a Moroccan guy, who knows? We probably have the same Harry Potter, in there. And then some people started implementing the idea. I think there's Green and Beam. I think they implement these ideas. I think they were competing to like implement that paper. But anyway, that paper is sort of a let's do a coin join at every block and try to mix all of the transactions together, to aggregate all the transactions, so that a block looks like a coin join. But the people creating that block, the validators or the miners or whatever, are going to see the individual transactions. They're going to see the graph. But after doing that coin join to like coin join the block, we're not going to see the graph anymore. And Mimblewimble has like a very nice idea where they're like, well, we don't have to stop there. Then we can take a block and another block and do a coin join of that. And if you keep doing coin joins, basically your entire blockchain just is one coin join, one big transaction with all the inputs and all the outputs. And I guess they have this already here. Yeah, Mimblewimble. Is that a thing in Harry Potter? No. Sounds like it could be. Huh?
Isn't that like the spell that makes people not be able to speak?
Oh, you're right. That's the spell from when they had that dark arts professor who was a fraud.
Oh, so it is
That was the fourth one.
Yeah.
And they were doing like, yeah, you're right. Because I think it's the brothers that like came up with that spell, like the twin brothers.
Should we talk about that now? That sounds more interesting. So anyway, this thing, they call it cut through, I think they call it. They could have called it compression, but is that how you write through? No. They call it cut through, and basically it's the idea of like merging, doing this successive coin join every time, and especially it's like if you reuse, it's kind of a transitivity thing where it's like you create a coin, you spend it in a transaction, you send it to someone else, and then if another transaction you send it again, you can sort of like cancel it in the middle. I don't know if that makes any sense, but that's what they call cut through, and you're sort of optimizing things when they appear in both input and outputs. You can remove them. The way it works is basically if I remember correctly, Mimblewimble like removes signatures, and basically they say we're gonna use only Pederson commitments. If you know the opening of a commitment, so it's here, right? That's my commitments with V and R. If you know the opening of a commitment, then you can spend it. And then they say, we're gonna create this equation. Maybe I'll rewrite here. The sum of the inputs minus the sum of the outputs. And we're gonna prove to you that it's equal to 0. But we're gonna do it in a weird way. I can't remember exactly how it works, but where the outputs are going to be like outputs that you want to send to someone, right? Like if Alice wants to send outputs to Bob, they have to let Bob create some of the outputs, which are Pederson commitments. And so you're going to have something at the end that's going to look like a commitment to 0 with like some blinding factor that I believe only the recipient knows. And the way they do it, and this is interesting because I think Zcash does it and maybe some other people do it, I think Monero does it as well, is that they're going to look at this thing here at the end. So again, this is a commitment to 0, but it has a blinding factor that's, so it's 0 here, right? But it has a blinding factor here. And they're going to pretend that this is a private key. And this private key multiplied by G is a public key. And so the only thing they do is that they prove knowledge of that. I think they do a signature actually of, they sign something using that private key. And you can verify it with this public key. And the whole thing about Mimblewimble is trying to figure out, so apparently all the papers had some bugs in it, and they're not very rigorous, and but there's way to make it work. It's all about figuring out how can you create some outputs with Bob in a non-interactive fashion. So we want to use inputs from Alice, some output from Bob and Alice, because Alice wants to send back some change, while revealing this to Bob so that they can use it to sign the transaction. So that's the first thing that they try to figure out in Mimblewimble. The other thing is like, how do we aggregate all of these transactions together? And basically, I think they use like pairings and this kind of like BLS signature scheme where you can just aggregate signatures and you can potentially aggregate public keys. I think they don't do it. I don't know why. And you're sort of aggregating all of these equations together. That's all I'm gonna say because that's all I understood when I was looking at it, and also I want to talk about other stuff. But that should give you an idea if you want to like dig deeper into that. All right, any question on that? I guess. I know it's kind of fuzzy, but yeah. So I wrote it as CoinJoin meets CT. So CoinJoin where you're like doing CoinJoin, but everything's a Pederson commitment, like in CT, in the confidential transfers. So you can clearly tell that this is where these guys came from. All right, the other one that's interesting is Monero. And basically Monero came from CryptoNotes and CT. So CryptoNote was like, how can we mask the sender and the recipient without masking the amounts? So these two guys. And how can we mask the amounts? And for masking the amounts, it's pretty easy. You just use Pederson commitments and range proofs. And so I know I'm running out of room here, but let me try to find some room here. So CryptoNotes. So let's split it in two. Sender, recipients. Do people actually know what they use for recipients here? It's also another term that's pretty famous in the stealth address, yeah? 1 point there. So stealth addresses are basically the concept of reusing a new address for every coin you send, but you don't want to have to reuse a new address in a way that's like imagine if you're a merchant, you want to like publicize your address and you want everybody to use it every time, right? You want to have a QR code or something like that, or put your address on a website, and you want people to be able to send you coins every time without having to like create a new address for people that want to send you something. So stealth address is a way that allows someone to create a new address for you from your fixed address. There is another notion of that in QuizQuiz actually, which is interesting as well, and they call it QuizQuiz. That sounds like another Harry Potter thing. They call it updatable public keys. But all of these things are very updatable pub keys. Maybe I'll start with this one because I haven't seen it elsewhere from QuizQuiz. But every public key is basically a randomized base. So what notation should I use? Addition or? All right, we'll do that. So you randomize a base, and then you use it to create a public key. Right? That's your public key. That make sense? Random base, you use the random base to create a public key. When someone wants to send you something, they'll generate some, they'll re-randomize your base, let's say with a R prime. And so they'll create R prime times R times G, and then they'll make your this thing, right? And R prime A is exactly A times the new base, right? So how do you check if someone sent you some money here? Like imagine you own A, the private key here, and you see a transaction that is sending to this address. How can you check if it's for you?
Trial decryption?
I wouldn't call it decryption, but I mean, that's more like in Zcash, I guess.
Strip off the R's and A's.
You can strip off the R. I mean, I guess you could strip off the R's, but that's not going to help you, I guess. So no.
Sure, the base point is just R times G. So you just verify the signature like this.
There's no signature here. It's just this is a public key and this is the base point, right? And they give you a randomized base point and a randomized public key.
So if you multiply by A,
Yes, right? No tricks. So you take this guy, the randomized generator, you multiply it by this little a. If it gives you that part, then you know it's for you. Right? You recreated your public key and it matches the public key. And so you know the private key of this thing, which is just a, right? So you can spend that. You can spend a coin that was sent to you. So that's updatable pub keys. I'm gonna leave it at that because I want to explain stealth addresses. But if you want, you can think more about that yeah, I didn't tell you what signature scheme, but all these signature schemes work the same way. So, okay, stealth address. It's very similar, except that your address is your key pair is like that, right? We're gonna reuse the same notation. And when someone wants to create a stealth address for you, they're gonna do a key exchange with you. So in a transaction, you'll see so in a Monero transaction or CryptoNode transaction, you'll see there's a pub key, or it's really an ephemeral pub key, which is R times G. They do a key exchange with you. So what's the key exchange? Is R times A. And what do they do with that? R times J times G, and they add it to your public key. I think that's how they do it. Right. So they call that the destination public key.
Yeah, I don't think we need R times A. Yeah, the beginning, just R times G. You can't multiply it.
No, this is correct, right?
Yeah, this
So we're gonna hash this. So basically, we want to derive a shared secret, and we'll. I'm wondering if this is, or maybe they do it like this. I don't remember. Well, it doesn't matter too much. Forget my confusion here. It doesn't matter how because actually it's a bit of a different scheme. But just to recap, they do a key exchange here. They derive a shared secret with an H. They multiply that with G, and they add that to your original public key. Whenever you see transactions, what you can do is that you can try to see if you can do a key exchange with that public key and recover that destination public key. And if you can do a key exchange with the public key and recover that, you can also recover the private key. You can think about it, but the math checks out. And well, any question before I actually show you the actual stealth address that you use? Maybe an interesting thing that they do is that actually your public key is going to be A and B, and here they add it with the public key B. That's a small change, but what it allows you to do is that you can give the private key of A to someone. They can scan the blockchain, so they can do the key exchange and see if they can recreate this public key, but they cannot spend it because they don't know the private key behind B. And so with that small change, you get a viewing key and a spending key, I guess. Does that make sense? So, yeah, any question on these stealth addresses? Again, you're just creating new random addresses that look completely random, undistinguishable from the original public key, and that hides the recipient.
Is it possible to break linkability with these stealth addresses to transact? I'm assuming that the rotation of these stealth addresses is the important part, right?
Well, so I think the network will detect if someone is trying to send to a key that they've seen before. I think there's something that enforces that you always use new things. Cool. And so the other thing about the sender, so we haven't masked who the sender is. So I guess that there's another buzzword someone wants to tell me. Ring signatures. Ring signatures. And so here, this is where we introduce the concept of K anonymity that you might have heard. So ring signature is basically, I'm gonna spend a coin, a Pederson commitment coin, right? And I'm gonna spend it by signing it with one of these stealth address. Like someone send me something using a stealth address, I'm gonna use the private key from that. I'm gonna sign it, like in a good old normal, like Bitcoin, whatever. Except that I'm gonna, since people can see me, I'm gonna do a bit more than that. I'm gonna find other public keys, basically decoy public keys that are on chain and their own commitments. And I'm gonna use this ring of signature, this ring of public keys to sign the transactions. And so with these ring signature schemes, as long as you know one of the private key, you can sign this thing as part of a ring of public keys. Maybe I can write it down, but I'll go here. This is your public key, and you want to like sign a transaction. You're gonna get some decoys, PK1, and they use 15 decoys, I believe. So you use a set of 16 public keys to mask yourself in this set of public keys. And this is what they call, I guess I didn't write it. This is what they call K anonymity, where K here is 16 in Monero. I believe that's the number they're using. Does that make sense? I'm not going to explain how ring signatures work. It's a bit complicated, but that's basically what's happening here. And there's a bit more complexity on like exactly who is signing. They're reusing that trick where you look at the excess. I think they call it the excess public key, so the blinding thing that you get at the end. And so you're going to use that to sign it. Like that's going to be one of the key to sign with. So when you use these decoys guys with their own commitments, you're going to get bullshit stuff that you don't know the private key of. But you'll have one of the private keys, so you'll be able to sign the stuff. There is some interesting de-anonymization attacks. Did people see any of that? That's really interesting. So Chainalysis. So Chainalysis is like a company that's doing de-anonymization. I don't know why I'm doing some advertisement for them here. Chainalysis, maybe? I don't know. And it's ethically a gray area, but they're presumably have uncovered a lot of fraudsters by running nodes in Monero. And so when you want to find keys, decoy keys in Monero, so like mask your own key, a lot of people will just query some nodes, some of these public nodes. And these public nodes were, poisoned, and basically they'll return decoy public keys that they own. And so when they see a transaction with their own decoy public keys, they'll know that you're this guy. And that's like the easiest way to the most naive way you could have thought of attacking the system. That's what they're doing. It seems like it's working really well. And yeah. So maybe, and this is why a lot of people like Zcash, I guess, because you get total anonymity, and we can talk about that as well. Actually, I don't know how much time have I spent on. Do I have a lot of time left? Okay. I can try to speed run, but any question on the CryptoNotes plus CT equals Monero / ring CT?
So if you run your own node from Monero, you can't, the Chainalysis attack isn't really super relevant, right?
Yeah, if you run your node, you're fine. There's other attacks, but.
Is it possible to do this with any of the other privacy solutions? Or is it just Monero's nodes?
So you mean these kind of attacks?
Yeah.
You'll see that I want to get to Zether at some point, so there's an anonymous Zether kind of thing. But here I think I think you could do something like that, where maybe I'll mention it when I talk about Zether, but there's a similar thing there. Basically, whenever you're in this setting of K anonymity, or like CoinJoin or anything like that, the other people might just be decoys that are poisoned or. Yeah.
You have also a double spending problem in the signatures. Because if you sign on behalf of the group, you need a way to.
Right. Okay. So I think I see where you're getting at, and this is very important. I need to mention it. Thank you. So you sign. You have you don't know who signed and spent the coins, right? The inputs. And so you need to make sure that these guys can still spend their inputs. And so in Monero, you have this idea of nullifiers, the same stuff that we've seen in E-Cash, right, with the blind signatures. When you do these kind of ring signatures, you're going to produce these things they call key images, but these are, you can think of it as nullifiers. They're values that the network needs to keep around. And when they see other transactions, they need to check that they haven't seen that before. And this is really annoying, these kind of cryptocurrencies, because this set of nullifiers keeps on growing forever. And I guess there's ways to try not to have it grow forever and new research in that area. But I'm not going to talk about that. But yeah, so where is Monero here? Cryptonote or Monero, we have these key images, and they're sort of nullifiers. So they don't tell you exactly who spent here, but they're deterministically derived, and so whenever this guy is going to want to spend, they're always going to produce the same nullifier, so they're not going to be able to double spend. If the other guy tries to spend, it's going to produce a different nullifier. All right, so let's go to, I just wanted to mention TEEs very, very briefly. So TEEs are, chips that presumably you shouldn't be able to look at what they're doing inside. It's pure hardware, and you can encrypt these keys. These chips can produce public keys. You can encrypt to these public keys. They can do some computation. They can decrypt the stuff you send them, do some computation, and then produce an attestation that they did the correct computation on them. So these TEEs are basically like zero-knowledge proof, like a server that you trust, creating a zero-knowledge proof at the end. That's how I think about them. MobileCoin has a very interesting scheme where basically they say, okay, in our network, everybody runs TEEs. So validators or miners run TEEs. When you want to send a transaction to the network, you'll send it to they'll basically do I think they do a coin join or something like that. Yeah, I think they do a coin join with whoever encrypted their transaction to the TEE, but inside the TEE, so you cannot see exactly what's happening. The thing is, if the TEE breaks, which is a legitimate, worry that people have these days, the coin join that is being done inside is actually done with the ring signature. And so if the TEE actually breaks, or there's a malicious miner, they have to prove to you that they have TEEs, right? But if there's a malicious miner and they get to see the TEE, they'll only see ring signature stuff. So you go down to K anonymity. So that's an interesting. There's many easy ways to do things with TEEs, but this one, MobileCoin goes one step further and does it so that if the TEE breaks, you still go down to Monero type of security. All right, all good. I guess I think I spent a lot of time, so maybe I can go over Zcash, Zether very quickly, and I can forget about the rest. Any question on stuff that we've seen so far? All right, so let me speed run the. Where should I do that? I'll do that here. Up. So. Okay, so in Zcash, they basically say, back to the show me and coins, you're gonna have these UUIDs, these random random string, let's say C1. But I'm not gonna sign it, I'm gonna commit to it. Maybe I can write it like this. Oh. I'm gonna commit to it. And when I'm gonna want to spend it, I'm gonna prove to you that this commitment exists. So there's a bag of commitments, like a UTXO bag, I guess. You're going to prove that this commitment exists and that you know what is inside. Actually, you don't need to prove that it exists. Everybody can see it in this model. But you're going to prove that you know what is inside. So you're going to do a zero-knowledge proof that you know what's inside. That by itself is sort of like show me and coin. And you can send that to someone, and that someone sort of has to do the same proof very quickly to create another one for themselves, because you know the opening of the commitment, so they need to convert it to their own commitments. This is very show me and coin like. Does that make sense? This small explanation. You generate a random value, you commit to it. The network accepts it because you transferred some Bitcoin to the network, or like whatever. And then you can just give it someone. They can prove the zero knowledge proof that they know that, and a zero knowledge proof that they create a new commitment that has the same value here. I guess you can. So it sucks. So you only mask the values so far, and you have this kind of problem. So another thing you can do is like you can include the public key of the sender. So, sorry. So this is the public key of Alice. What you can do is that you can include the public key of who you're sending it to. So here you're saying here, I prove to you that there's a commitment. The network has this UTXO, that's a commitment. Inside of it, I'm not showing you what it is, but inside of it, there's a C1 that's the same as the new commitment I want to create. And also there is a public key, and I know the private key of this thing. And then you put the public key here. And that's basically the second step of Zcash. I don't have the best explanation, but bear with me. The third thing that Zcash does is that it puts this inside a Merkle tree, so that basically you don't know, the proof is not just, hey, here, look at the commitment, that's the commitment I want to use. The proof is, there is a commitment at some point in the Merkle tree of commitments. I'm not saying where it is in the roots. So now you're really masking the sender, sort of. You don't even know what is being used, but you know that it exists in the Merkle tree, and also you know that it hasn't been used before because you maybe there's a serial number, and you reveal this thing. And there's some issues if you do it this way like that, but you can think of it as revealing this thing is basically like a nullifier. This is the most naive way of doing it. And this prevents you from double spending that coin in the future. I think I can get away by just saying that for like the early Zcash schemes. And then they start using like more interesting schemes with like Pederson commitments and stuff like that. But the early Zcash proposal was just use a Merkle tree. Whenever you create a commitment, put it in the Merkle tree so that when someone wants to spend it, you don't know which commitment it is. Create a nullifier when you spend that commitment so that it cannot be double spent. And include like a public key inside the commitment so that only when you create a coin for someone else, only they can spend it. And again, you have this same problem here where you have to scan the blockchain. I don't know if I really emphasized that earlier, but you never know when someone sends you something unless they tell you off-pen that they send it to you and they're like, this is the commitment for you, and this is the openings. So the earlier you had to do a key exchange to like figure out if it was, or like produce a public key and see if it was yours, or do a key exchange to figure out if a transaction was for you. In Zcash, you have to, the way they did it is that they encrypt what's in the commitments to your public key, and you have to do this trial decryption where like for every transaction you see on the blockchain, you have to trial decrypt and see if it's for you. And I guess they have the same thing where they have you can sort of delegate someone else to do it, and so they have this kind of like what we saw with the stealth address. They have a key just to view and trial decrypt and a key to spend. But that's basically my 5-minute intro to Zcash or Zero Cash or Zcash, like all these shielded pool kind of things. Okay, any question? And then I'm gonna jump to Zether and then I'm gonna stop there. That's a lot of schemes in one. Oh, there's 2 of these. There's enough space. All right. Yeah, no questions? All good on Zcash stuff?
You said Zcash might have changed?
I mean, Zcash changed so much that I don't really know what Zcash is today, to be honest. But my understanding is that I think they even have like tokens, what I was saying with the hash of a token ID. Does someone know? Maybe, can't really know. Okay.
There's talk of changing that. I'm not sure if any consideration has been put into the current mainnet for that though. Maybe.
Yeah. I mean, there's been to my understanding, there's been a lot of changes over the years.
Yeah, they even combine all this like homomorphic stuff with the nodes, and like there's a lot of interesting stuff.
Right, where they use this thing as private key to sign. But essentially the IDs are always sort of the same IDs and like reused and like combined in different ways. And I haven't even mentioned the zero knowledge proof schemes and like what they use. Cool. Okay, Zether in like 2 minutes. I can do this. So Zether is the first account-based, like one of the only account-based system. Everything else that I've talked before is sort of UTXO based. Like we're creating coins, we're spending coins. In Zether, we're account-based. So I'm not gonna use David. I'm gonna use Alice. Alice has some balance. Bob has some balance. And so here we're already giving up on like sender and recipients, linkability, all of these things, right? We're only masking amounts. So again, like really all these schemes, they always do some of them, all of them, maybe with key anonymity for Monero, maybe with total anonymity for Zcash. By the way, total anonymity because you're hidden in that Merkle tree, so nobody ever knows who you're sending to or who's gonna spend that coin. In Zether, you're account-based. You already know, you're only basically encrypting these amounts. The encryption you're using is Elgamal encryption. So, here this encryption is B1 times G times A times G. And here this is B2 times, so this is your public key, right? Is it, I hope this is how I remember it. But if you want to send money, so everything's encrypted with a homomorphic encryption scheme that is additively homomorphic, so you can subtract and add two balances. If Alice wants to send something, basically she has to create a transaction that encrypts the amounts that she wants to transact with, and she'll encrypt that both to her public key and to Bob's public key. And I mean, maybe let me even do it without even talking about Elgamal. This way, it's going to be super easy. But the way you do this, like the network is going to do, basically they're going to homomorphically subtract the value from your balance here, and they're going to add it here. But again, this is encrypted with like Bob public key, and this is encrypted with Alice public key. So but does that make sense? The homomorphic stuff, it's pretty easy. Like everything's encrypted, you can add stuff or subtract stuff, and it keeps it around. What's important is that this system is actually, there's a lot of implementation detail. No, I mean, it's not implementation detail, but there's a lot of details to make it right. But of course, you have these range proofs because you don't want things to like overwrap or underwrap and these kind of things. Here, you want to make sure that this subtraction here doesn't underwrap, so you have a range proof on the results, and you have to define what's a negative value and these kind of things. You have a proof that proves that these two encryption encrypt the same value. And then there's a lot of other implementation details. Like Zether spends a lot of time on like, if you have 64-bit values, how do you decrypt? So decrypting with Elgamal is annoying because you have to like solve a discrete log. So you can split your encrypted amounts by like 32-bit, and like try to re-add them after. If someone front runs you, it kind of invalidates all your zero knowledge proofs. So you have like, you can split your balances between current balance and pending balance. So there's a bunch of machinery to make it work, is what I'm saying. So Zether has this, I mentioned it earlier, they have this anonymous Zether variants where you choose a number of accounts, including, as decoys for accounts that are gonna send and accounts that are gonna receive. And basically for the decoy accounts, you'll you'll do a transaction of 0. So you're not gonna change anything in these accounts. You subtract 0 and you add 0. But from an external viewer, it'll look like you're modifying a bunch of accounts. You don't know which one has an actual value being subtracted. Okay. Yeah, any question on, on Zether in 2 minutes? I guess that was 5 minutes, but. And I guess I'm gonna skip the MPC FHE. Just know that there's other ways to do it in MPC and FHE. Usually like Zether, where instead of encrypting this is FHE, this is HE, homomorphic encryption, but you can also do it with FHE, I guess. And yeah, that's all. I'll stop here. Yeah, that's a lot. Cool. All right, thanks.